taught over the centuries is that in the end, the articulation of the question is often as interesting as the answer. Indeed, Professor Knoll has himself defined science as a disciplined way of asking about the unknown. So, are we alone in the universe? Whether to ask or to answer, it is my distinct honor to ask you to join me in welcoming Professor Andrew Knoll.
Thank you very much for that kind introduction. I should say it's a great pleasure to be here tonight. It's a real pleasure to be in this wonderful new auditorium, and it's a real privilege, I think, to give the Sokol lecture. Tonight, as you've already heard, I'm going to discuss at least aspects of what must be one of humanity's oldest questions. Are we alone in the universe? Our grandparents asked that question, their grandparents before them. But we live at a privileged time, however, in that we are probably the first generation in human history, certainly unlike our parents' generation or our grandparents' generation or their early ancestors before them, that we can go beyond the wonderment of a starry night and reframe our curiosity in terms of scientific questions that can be addressed through a program of exploration and research. In fact, we live at a moment of great astrobiological optimism. Almost every month a new book appears which tells us what life might look like in the interior of Mars, or how organisms could be living beneath the icy veneer of Europa. In fact, the Australian physicist Paul Davies has gone so far as to declare that we're all Martians, descended from some bacterial immigrant that came to Earth via meteorite. There's a certain flavor to all of this literature, however. It could have been, might have been. And I always bring to mind a quote from the French writer André Gide, who said that fiction is history that might have happened. So the real question is, how do we have a program of observation and research that can really sort astrobiological fact from fiction? And so what I'd like to do tonight is, rather than ask about the whole panoply of questions that might engage our curiosity on life in the universe, and I'll certainly be happy to try and address any questions over that whole gamut at the end of the lecture, but I'm going to actually focus on one area where recent discoveries, in fact discoveries that are continuing literally as we are together this evening, are really reshaping our thinking about one specific question. And that question is, was Mars ever a biological planet? And I won't leave you in suspense. The proper answer is we haven't a clue. We don't know whether Mars was ever a biological planet. But what I'd like to do tonight is talk to you in particular about how the current NASA Mars explorational Rover missions, which have been active since January, are helping us to rephrase that question by telling us something about the environmental history of our planetary neighbor, and in a way that is certainly going to constrain our thinking about any life that may or may not have originated on Mars. Let's start out on our own planet, the one place in the universe where we actually know something factual about life. The great thing about our planet, to me as a paleontologist, is that it is a planet that records its own history. And that history, seen here, there you go, in the left-hand side, is written in sedimentary rocks, sandstones, limestones, shales, that are deposited one atop another through our planet's history. In those rocks, we find chemical clues to what past environments were like, and as you see from that trilobite on the right, we also find aspects of Earth's biological history encoded in rocks. Now it turns out that if you look for conventional fossils of conventional animal and plant life on this planet, you can go back only about 15% of the way into our planet's deep past. The oldest trilobites are about 520 million years old. The oldest evidence of any animals whatsoever date back to less than 600 million years. Yet our planet is more than 4.5 billion years old. And one might wish to ask, for what portion of this immensely long history of our planet was Earth, in fact, a biological planet? We can actually ask those questions and get answers because it turns out that there is a good sedimentary rock record of Earth's deeper history, seen in that picture in the left. That's an outcropping of rock in the glaciated highlands of Spitsbergen, which is an island about halfway between Norway and the North Pole. Immensely rich outcroppings of rock that predate the first appearance of animals. If you look through those rocks, you can look for a long time and you will never find any shells, any bones, any tracks or trails of animals. Yet, as we've looked at these kind of rocks carefully, a tractable, interpretable signal of biological activity has become apparent. In the lower left, you'll see that there are actually fossils of tiny microbial life that abounded in the seas at the time these rocks were formed. They're about 700 to 800 million years old. Each of the little fossils that you see in those aggregates of spheres is only about 4 microns in diameter. Terribly tiny, yet they preserve an unambiguous record of biology. Not only do we have morphological fossils preserved in these ancient rocks, but there are actual biochemical fossils, molecules, organic molecules that were synthesized by known groups of microorganisms that are actually preserved in the geologic record. I was saying to someone tonight at dinner that when we all die, the last part of us to remain as a testament to our existence will be our cholesterol. And in fact, you can look at these rocks and find cholesterol, or at least the geologic derivatives of cholesterol, and other similar types of molecules made by algae, bacteria, protozoa in the early oceans. We can expand our purview a little bit wider and look not on that microscopic scale, but look on the scale of things you can see with the naked eye. In the upper right-hand portion of the picture is actually a sedimentary expression of biological activity. These layered structures that dome upward are actually well known to be hallmarks of interactions between microbial communities that form mats on the seafloor and sedimentary processes themselves. In fact, there are, in the deep Earth history, there are records of reefs built by bacteria that are almost as large as the Great Barrier Reef today. And then finally, the picture on the lower right, which I won't go into detail, is really meant to convey the fact that although bacteria are individually tiny, they are so populous and so abundant that their activities can actually change the chemistry of seawater and change it in a way that can be recorded in limestones and organic matter preserved through time. So what we've learned is that for long eons before the sort of large and conspicuous fossils of animals and plants were deposited, Earth was indeed a biological planet. We can find a tractable history of microbial life that extends back more than 3 billion years on this planet. From that, I infer that in fact biology really should not be thought of as something that is separate from the planet on which it resides. Biology is very much a planetary phenomenon. We believe that life was born of planetary processes early in our planet's history. Life has certainly been sustained over the eons by planetary processes like plate tectonics that continually renew the supplies of materials that are needed to sustain living communities. And quite remarkably, on our planet, life has actually emerged as a suite of planetary processes important in its own right. When this planet was young, there was no oxygen in the atmosphere. The oxygen exists in the atmosphere for the simple reason that we have organisms that are capable of photosynthesis, which produces oxygen as a byproduct. So if you buy that idea that life is an inherently planetary phenomenon, the next question is simple but a fairly large one. What about Mars? Now, I have to tell you how I got involved in Martian work. For most of my career, I have been happily earthbound. There's plenty to do on this planet, enough to keep someone like me busy. But about 7 years ago, I guess, I was at a meeting in Washington, and I met a young planetary geologist from Cornell named Steve Squires. And Steve sort of came up to me and made small talk for, I'd say, about 25 seconds or so. And then he said, would you like to be on a Mars mission? And so sort of in the spirit of the conversation, I said, yeah, sure, why not? And little did I know that was going to change my life in a very important way. Soon thereafter, we did submit a proposal, and by we, I mean mostly Steve and his instrument building colleagues, and much less me, that actually then got chosen as the instrument package to be flown on the Mars explorational rovers, which, as some of you will know, landed on Mars in January and are happily chugging along in about for one of them, the 290th day of operation. Now, we can think about life in two ways on Mars. One thing we would love to know is there life there today? If we go to Mars, can we find something that by some definition, not necessarily our own, we have to acknowledge is living? Well, if you look at that picture, which is a Gusev crater on the Martian equator taken a few months ago, you would be tempted to think, that doesn't look like a very promising area for life. And you're correct. It's an awful place to think about life. It is exceedingly cold, although I will note with some sorrow that there was a day in early January when the noontime temperature on Gusev was actually higher than the overnight temperature in Boston. But at Boston, that's something that happened once in every 30 years. On Gusev, it's a way of life. There's simply no liquid water. It's too cold. Very, very dry. The sediments are harshly oxidizing. They're called caustic sediments surface. And there is harmful radiation bombarding the planet all the time. I think the likelihood that there's anything living today on the surface of Mars is quite remote. On the other hand, we've known for almost 30 years now that Mars may have been somewhat different early in its history. And the reason we know that can be summed up in the pictures that you see in the slides. That is, beginning with the Viking mission in the 1970s, in that picture on the left, planetary scientists learned that the Martian surface is covered by features like drainage systems, channels, that tell us that liquid water flowed on the Martian surface at one time in its history. And that has been reinforced by increasingly highly resolved photographs that have been taken by more recent imagers, particularly a camera on the Mars Global Surveyor, which remains in operation. And you can see on that upper right-hand picture that you have these large channels, which if you look closely actually has a thin channel inside it that seems to have been cut by water. And the orbital picture on the lower left, you can see streamlining that is, I think, on Earth clearly the hallmark of moving liquids that are shaping the landscape. So at one time, Mars may have been different from the Earth. The other thing that we've learned about Mars through orbital images is that, somewhat surprisingly, I think, to a lot of us, Mars has a lot of evidence of layered rocks. That is, just like our own planet, there is a history of the Martian surface encrypted in layered rocks, and that if we can go there, we might be able to learn something about them. Well, this is our virtual geologist. In fact, it's part of a set of identical twins which are working on Mars now, Spirit and Opportunity. Let me just tell you a little bit about how this geologist works. It is about 1 meter high, so it's about waist high. You can see in the center, it gets its energy supply from the sun, has solar batteries. You can see the solar panels. The round tambourine-like thing on the right is a set of antennas that it uses to communicate with the Earth on a daily basis. You can see there's a nice wheel and sort of rocker assembly that allows us to move fairly efficiently over a cobbly, at least, landscape. And the real science that's done by this rover is done on that mast that you see sticking up and the little arm that you see sticking out in front of the rover, looking curiously at that rock. The mast has a series of instruments on it, a series of cameras, some of which are used for navigational purposes, others of which, something called the PanCam, or Panoramic camera, is an extremely high-resolution camera that has, I think, 13 monochromatic filters, so you can take color pictures, you can bias the pictures you take towards different wavelengths, so you can accentuate different features that you might want to see. There's also a reconnaissance chemical instrument on that mast, something called the mini-TESS, TESS being short for thermal emission spectrometer. And what that means in English is that rocks basically emit heat radiation, and infrared radiation, and the kind of radiation and the wavelength of that radiation emitted by rocks or other materials is a function of the chemistry and mineralogy of the rocks. So what mini-TESS does is it sort of stares at a rock, and from that it is able to measure a spectrum of radiation coming from that rock, and then by comparing that to a known library of materials that have been analyzed on Earth, you can make some inference as to what the chemistry of the rock was. So that's our sort of reconnaissance geologist. But if you really want to know something in detail about the materials that you encounter on Mars, you have to use that little instrument arm in the front. That also has a series of instruments on it. On the one hand, it has something called the RAT, which is a rock abrasion tool, which is a very simple but very effective instrument. It's basically a brush and a drill. One of the things that was learned in the 1997 Pathfinder mission to Mars was, where there was no facility to brush off the surface, is that pretty much all of the chemical analyses of rocks that were taken on that mission turned out to be a mixture of rock and surface dust. It's very hard in some ways to deconvolute that and find out what the actual composition of the rock is. So the RAT just brushes off the dust. Also, because there is, not only in theory, but in practice, a very thin rind of surface chemical alteration on most Martian surface rocks, it would be nice to drill down or grind down, a couple millimeters into the surface so that you can, A, get a measurement of the pristine chemistry of the rock, and then B, compare that to the surface chemistry to try and learn about processes that have altered the rock through time. And the RAT does that as well. So that's been a really wonderful instrument. Other instruments on that instrument arm are something called a microscopic imager, which is about like the hand lens that a geologist uses to get a microscopic view of a rock or soil. And then there's two other chemical instruments. One's called a Mossbauer spectrometer, which is very useful for telling the mineral composition of sediments or rocks, but only for minerals that contain the element iron in them. It turns out that that's not too debilitating on Mars because iron is a very important constituent of much of the mineralogy. And then finally, there's another instrument called APXS, which is a NASA acronym for Alpha Proton Xray Spectrometer. And what that is able to do, again, is it bombards a sample with an X-ray, and when it then looks at the spectrum of materials that are emitted back by the bombarded rock, and that actually can tell you the chemical composition of a rock, the percentage of many different elements that are present in the rock with very good resolution. So that's the geologist. It can move, it can take pictures, it can take microscopic pictures, and it can tell us something about chemical composition. It's a very efficient rover for doing reconnaissance geology, for learning something about Mars' environment. It was not designed as a life detection rover, and certainly lacks some capabilities that you might wish to have were you asking specifically and directly questions about life. But we'll come back to what's needed for the future missions in a minute. I like this picture because it kind of shows a family tree of rovers. Many of you will remember the excitement of Pathfinder in 1997. Pathfinder is, or at least one of the versions of Pathfinder, is that little guy in the front, on the left-hand side of the picture, with opportunity staring down sort of in a superior way from below it. The capabilities of these rovers are quite different. Over the entire length of its mission, Pathfinder moved about 50 meters, and most of that was going around in circles. As of yesterday, the Spirit rover in Gusev Crater today on Mars has gone something over 3.5 kilometers, and Opportunity rover has gone about 1.7 kilometers. So these have been, relative to the previous mission, extraordinarily mobile rovers as well. Now, the one question you might want to ask is, how do you pick the site for a Mars landing? Why should we go to one place in preference to another? And I have to tell you, there's 3 major considerations that for site choice, only one of which is scientific. In the first place, you notice that the energy supply for this rover comes from solar panels, and it's a solar battery. What that means in practical purposes is that you have to land within about 15 degrees of the Martian equator, or you simply, over the course of a season, cannot keep regaining energy lost by counting on the power of the sun. So right away, just because of the energy balance of the rover, you've cut out about 90% of the Martian surface from consideration. The second consideration is safety in landing. And if you think about it, that's fairly simple. You can only pinpoint landing accuracy to within an ellipse that's about 70 kilometers long and maybe 20 kilometers wide. In order to feel safe about landing, the entire area of that ellipse has to be pretty flat. Ask where to land in the United States. Any geologist would say the Grand Canyon. Any engineer would say Kansas. And I'll tell you, the engineers win every time. So again, of the areas near the Martian equator, only a relatively small percentage was deemed feasible to even think about landing from the standpoint of engineering safety. So with that in mind, then, finally the geologists can come in and say, well, where's the best science? And so the 2 sites that were chosen, both near the Martian equator, were Gusev Crater on the right corner of the slide, which was chosen because it was initially thought that perhaps that crater had once been a lake and would give evidence of water and water-related processes. As it turns out, Gusev's told us a lot, but there is not a great deal of evidence supporting the idea that it was a lake surface. The other rover, the one that I'm going to talk about most, because it's A, the rover that I worked on the most, and B, the one that's most germane to questions of biology and environmental history, is the one in the middle of the slide on Meridiani Planum. So why did we go to Meridiani Planum? For a very particular reason that becomes clear when you understand what this slide, which is an overlay of several different things, is trying to tell us. First, if you just look at the topography, Meridiani Planum is flat. In fact, it's really flat, flatter than most surfaces that you can think of in the United States today, and that includes Ohio. Northern Ohio, at least. The second, and you can see the landing ellipse in there, that is the actual landing ellipse that was calculated for the landing spot in Meridiani Planum, and we actually landed very close to the center of that ellipse. It's a terrific testimony to the talent of the engineers who run this program at the Jet Propulsion Lab. But the thing that really commanded everyone's attention is what on this picture is shown in the various colors. Those colors are a gradient going from small concentrations at blue to higher concentrations in red. And it's a gradient of the abundance of the iron mineral hematite. It's an iron oxide mineral. It turns out hematite is really of interest to geologists because none of us could think of ways that you could make hematite without involving liquid water. So hematite then, because of this need one way or another, and there were several models, most of which turned out to be wrong, for generating that hematite was really the beacon that really made the entire Mars science team to agree that this is a place that we want to land. And I love this picture because it, again, shows a couple of things, not least of which is the extraordinary resolution of the cameras that are orbiting Mars today on the Mars Global Surveyor. If you look at that picture on the right, there's a fairly conspicuous crater. That's now called Endurance Crater. It's about 150 meters across. And as we sit here tonight, Opportunity is around the south, within that crater on the southern flank. If you look to the beneath that, you'll see there's a little dark item in a white circle. That turns out to be the heat shield from the lander. When basically the module that flew all the way to Mars had a heat shield. It has back top of the lander, and then once those peeled off, and you see the heat shield landing there, a bunch of balloons were opened automatically, and many of you have seen this, at least in the animation of it. Basically, this thing lands by bouncing along. And this has now been a successful way of landing sophisticated machinery on Mars twice. It really works. And what you can see in that large circle in the left of the center is those sort of three light areas are actually the first bounce mark of Opportunity lander when it hit the ground. Over to the left, there's the back shell and parachute. And then if you look where it says Opportunity lander, there's a small crater that's about 20 meters across. And there's a little white dot in that crater. That's actually the Opportunity lander that came to rest in this little crater. And I love this picture because it, among other things, tells you that there's some very, very highly educated engineers at JPL with time on their hands. What you can see, this is a quantitatively accurate picture of the landing trajectory of Opportunity. You see the thing comes banging down on the left, it bounces around, and then sort of like a Tiger Woods putt just goes right in that little crater. Now, in some ways, the most exciting moment of a mission like this is the first time you see a picture of a new terrain. And that was certainly true for both Spirit and Opportunity. On the bottom, you see the first view that we saw from Spirit when it landed on January 3rd. And I must say that when I looked at this, it was tremendously exciting, if only because we knew that we hadn't crashed. But when you look at this, you'd be forgiven for saying, yeah, that kind of looks like Mars. That is, there's a bunch of chunks of basaltic volcanics. That's the kind of lavas you would see on a Hawaiian volcano. And they're distributed around the surface, mainly appear to have been gardened by impact processes. There's a lot of red dust around. It is very much the picture of Mars that we saw on Pathfinder and the picture of Mars that Viking saw some years earlier. You can imagine our excitement then on the 24th of January when the first pictures from Opportunity Rover in Verdiani Planum came back. And that's that upper picture. It was unlike anything anyone had ever seen on the Martian surface. And for someone like me, it was particularly exciting because within a few seconds of that picture sort of flashing up on the big screens in the science room, we knew that we had landed within a few meters of layered rocks. That is, all the kinds of things we have been done over the years to interrogate Earth history by trying to understand the chemistry and texture of sedimentary rocks were going to be in play on Mars. Now, if that was the most exciting picture I think I can recall from the early days of the Mars rover, this is probably the most disappointing picture. This picture shows two things, one of which is tremendously interesting and uplifting, and the other one I found crushing when I first saw it. One of the great tools we have, software tools on this mission, is one in which the terrain of the Martian surface, as revealed in photographs, can be made into a three-dimensional map, which is what you see in gray. And then you can actually simulate the activity of the rover on that terrain. So what you do every day when you sort of make the list of commands to tell the rover what its job is going to be today, is that that day's mission then gets simulated, and quantitatively you can really see the accuracy of your pointing, whether you're likely to do successfully what you hope to do. So that's pretty neat. The disappointing part comes when you look at this terrain. When we first landed and saw that picture you saw in the last picture, I thought this was just a huge canyon of rock, that we had found something that was just, tremendously thick and interesting. Well, that little gray stuff underneath the front wheel of the rover is in fact that outcrop of rock that you saw in the last picture. It is an incredible 35 centimeters thick. Nonetheless, it's 35 centimeters of Mars, which makes it relatively interesting. Now, when you look at these rocks up close, you start to see some things that help us to interpret them in terms of the processes of deposition. The first thing that you see, and you can see very well in this picture, is that the rocks are made up of thin laminations, only about a millimeter thick. That tells us right away that we aren't dealing with volcanic lavas. These are likely to be sedimentary rocks. You can take that microscopic imager and look at these rocks, and you can see something else, and that is that the rock is made up of little round sub-millimeter pieces of material. In fact, these are sand grains. The rock is a sandstone. You can see the lamination is made up of these grains. Then we go to another level of observation, and it's a little bit hard to see, I'll admit, in the background picture here, but if you look closely at that sort of football-shaped rock, you'll see that most of the bedding of the rock is pretty even, going from left a little bit down to the right, but that if you look carefully, down in here, you'll see that there's a form of bedding which is running at angles to the main disposition of the beds. That's something that geologists call crossbedding, and it's something that happens when materials are deposited out of a fluid. Now, it turns out wind can cause crossbedding, and so can running water. Well, it turns out that the details of the crossbedding, at least, well, I should say that some of the crossbedding we see in these rocks does appear to have been formed by wind. Some of these are wind-blown deposits, not too surprising. But some of them are crossbeds that our experience on Earth and physical modeling confirms are only made in the presence of running water. So now we know three things about this rock. It's layered, it's a sedimentary rock, it's a sandstone, and it was deposited in part under the active agency of wind, but in part under flowing water. There's something else we can see. If you look at that outcrop picture in the lower left there, you'll see that there are small structures. They're really maybe a centimeter or two high, that just little like slits that go at various angles to the bedding. You can see the same thing in the upper right under the microscopic imager. And what those are what geologists call vugs, which are simply places where something has dissolved out, leaving a void. And they are voids that have the shape of crystals. In fact, for comparison, the picture on the lower right is a picture I took in some Cambrian rocks in Siberia, where those vugs form by the dissolution of calcium sulfate minerals, gypsum, if you will. And it's very likely that these structures that we see in these Martian rocks also formed by A, the formation, and B, the dissolution of very likely some kind of sulfate mineral, not dissimilar from gypsum. So now we know something else. Not only is it a sandstone deposited in part underwater, but that this has a history that goes beyond deposition to what geologists call diagenesis, that this rock is being bathed in water over a period of time. It's allowing crystals to precipitate out of water in the groundwater. It is further at some later time causing at least some of those minerals to dissolve. This rock has a real history to it. Now, I'm not going to expect you to understand all these wiggles on this particular slide, but it is the kind of data that's spit out by this alpha proton X-ray spectrometer. And what it does is gives us a quantitative sense of the elemental composition of these rocks. And from that, you can gauge what kind of rocks in general they are. And what we find is that about half of these rocks, these sandstones, about half of them is made up of material derived from basaltic lavas. Again, the kind of thing that would form in Hawaii today. That's not surprising. Mars is paved with basalt. But the other half was surprising. About 40% of this rock is made up of salts, mostly salts of sulfates, like gypsum, but some other things. And that tells us, again, something that was truly unanticipated. And that is, not only has there been water on the surface of Mars, but that water had to stick around enough and have extended chemical interactions with the rocks on the Martian surface, or just beneath the Martian surface. And so that therefore, this is a planet where water is having a chemical as well as a physical impact on the surface, and that was new. The other thing that's interesting, and it's what we might have guessed from the orbital measurements, is that that rock has about 10% by weight hematite, this iron oxide mineral. Also, when we looked at this, the iron mineralogy of this rock with the Mossbauer spectrometer, and again, I won't worry about the details of what these wiggles show, but what they show a Mossbauer spectrometrist is that one of the sulfate salts present in this rock is a mineral called jarosite. And jarosite is an arcane mineral, but it tells us something very important. If you look at places on our planet where jarosite forms, it only forms under acidic conditions. Usually jarosite forms in waters of about pH 2 or 3. It can go up a little higher, but usually it's very acidic. Just for comparison, your stomach acid is about pH 4. So these are pretty interesting waters. Now there's other constituents of this outcrop as well. One of the most interesting thing was something that we christened blueberries very early on, for reasons that will be pretty obvious from looking at that picture. Although honesty makes me tell you that they're actually not quite blue, they're more gray in a real color picture. But early on, as soon as the rover got off its lander and started moving around, we noticed that the surface of the soil was just studded by little 3 to 5 millimeter spheres. And when we got to the outcrop, we found that those spheres actually were coming out of these salty sandstones. So we became really interested in them. A number of features of them, from their distribution to things like that, where you can see several of them lined up with one another, to their relationship to the layers in the rock, tell us that these are what geologists call concretions. A concretion is a mineral structure that actually is nucleated within sediments and grows inside sediments. So again, that tells us that not only was there water present at the surface when these rocks were deposited, but that when these were young sediments, they were actually soaked in water for extensive periods of time. Now, one of the things you'd like to know is what the chemical composition of those blueberries is. Turns out that the blueberries are a good deal smaller than the sort of measurement spot size of the chemical instruments. So what you have to do is find a place like this, where you can find one area that is blueberry poor and an adjacent area that's blueberry rich. And so we were able to just clean off this part of this berry bowl, measure its chemistry, then do a chemical measurement here, and by comparing them, then you can get some sense of what this berry may have looked like. Again, this is Mossbauer data on the berry. The berry bowl, that is the part without berries, is this yellow bit here. And the berries themselves are this blue. And they differ very much in this set of signals that form the flanks of the central curve. And those turn out to be the identifiers for the mineral hematite. In fact, the berries, these concretions, are concretions of iron oxides that grew within the young sediments. Okay, so what do we know then about the rocks where we landed? First, the basic materials that give rise to this come from basalt, and there is a large mixture of sulfate salts, and again, the real source for that is volcanic sulfur mixed with water at the end of the day. That some of those salts include jarosite, which tells us this was a very acidic area, and that there's iron precipitation. And in fact, as we'll see, that iron is really the source of the hematite signal seen from orbit. There's evidence from the physical textures of the rock for flowing water. There's evidence from the chemical and textural evidence of the rocks for extensive and long-lasting groundwater within the sediments, and extensive chemical interactions between rock and water. And so when you put all these things together and say, what was this environment like, what you come out with, that it was probably something like a playa lake. That is, if you've ever been out to Las Vegas, you'll find that out in the outskirts, there are these thin pans of water that are lakes with water in them maybe once a year. But then the water dries out and salts actually precipitate. Well, that's the general idea here. There must have been replenishment of that water episodically over a period of time, but basically this was a basin where water was coming into the basin and then evaporating. But it wasn't quite like those lakes in Las Vegas, in that the waters tend to be very, very acidic. You might ask what the age of these rocks are. We don't know exactly, but by a fairly inexact method that looks at the distribution of craters both in the rocks underlying this package of sediments and on the surface of the sediments themselves, the broad guess is that these rocks were deposited 3 or 4 billion years ago. That is, to a first approximation, these rocks on Mars are about the same age as some of the oldest sedimentary rocks we can look at on Earth. The other thing that we have to think about is that, we know from a very careful surface mapping of rocks that this kind of rock is not common on the Martian surface. We have good maps of hematite, and basically there's this area in Meridiani Planum, which is about the size of Oklahoma, and it has this distinctive hematite signal. There's one other tiny area of the planet, and that's about it. Something in the mixture of conditions that gave rise to these sediments was only distributed regionally and not across the planet. And I tell you, if I had to make a guess, I would guess that was water. Okay, basically everything that I've told you about came from the first 60 or 70 days of the mission in this little crater called Eagle. About 60 days into the mission, we got our courage up and got out of the crater. First went to this place called Anatolia, where you can see these cracks in the surface. Then went to a very young crater called Fram, and then finally to Endurance. And as I say, as of today, opportunity is right about here, hopefully within the last month of being in this crater before striking some very different terrains in the south. I'll only say a word about what we saw as we went over the plains. Mainly, what we learned as we went over the plains was to confirm what the source of the signals that orbiters had seen from space. It's without doubt the source of that hematite that brought us to Meridiani Planum is these little blueberry concretions. They make up about 20% of the orbital signal. The other 80% is just sand made of basalt, so it's basically sand derived from the breakdown of lavas. And we can tell from the density of these berries on the surface of the Meridiani plain, how much outcrop had to erode to form those. You can see the outcrop eroding. Sand is whipping across the surface all the time. And it basically sandblasts these salty sandstones, and everything gets destroyed except for the little hematite nodules. They weather out. But this tells us that in 3 or 4 billion years, less than a meter of rock has been removed from the surface. And to a first approximation, this very flat surface that we see over this Oklahoma-sized area of Mars is actually the depositional top of these sandy beds. Now I have to show this picture because people tend to ask about it. When you look at this picture, the thing that I want you to see is the 2 wristwatches on our male model. It turns out that this was not because I was running for Geek of the Year or something like this. It was for a very practical reason, and that is the mission was and pretty much continues to be run on Mars time. What do you mean by that? It turns out that the Mars day is 24 hours and 39 minutes long. And so that means any given time on Mars will actually precess through the Earth day. Now that has a couple of consequences. You have to essentially stay on Mars time because the communications windows between Mars and Earth are tuned to the Martian day. Basically, you can communicate when the rover is facing toward the Earth. And so that means you can either say, well, today's meeting is going to start at 8 a.m., tomorrow's meeting is going to start at 8:39, the next day, 9:38, whatever. Or you can say the days we're on Mars time, and every day our communications meeting starts at 8 a.m. Clearly that's what you have to do in order to ensure effective communication. Because of that, we all got these wristwatches that actually keep Mars time, probably my happiest memento of the mission. And B, it meant we kept some very odd hours. I gotta say, it was actually kind of exciting to be up there. The Mars day, early in the mission, was starting, say, 2 or 3 a.m., and you sort of go up and huddle in this room in JPL, away from the world, and you felt like this band of brothers and sisters, and very exciting. The second time you sort of cycle through to 3 a.m. starts to your day, it is less exciting. And the third time, it's truly less exciting. Okay, let me just say a word then in concluding the sort of geological part of this, and then we'll get to the biological implications of this. But this is a picture of Endurance Crater, where we are now, and we've hung around Endurance Crater for a long time, because if you look up at the crater wall, this has something that we couldn't see from our first little Eagle crater, and that is there's actually a stratigraphy in this crater wall. And you can see it here on the left. There's at least 6 meters of sedimentary rocks exposed. At the bottom, you'll see that there are some laminae going that way at a fairly large angle to the major run of bedding. That's because those are basically sand dunes. So part of this, again, was clearly underlain by, or deposited by sand. But as we've gone carefully, and this is my favorite picture of Mars, this is actually the wall of, sort of southwest wall of Endurance Crater, and you can see the stratigraphy. You can see from the color there are different beds as you go down the wall, just like you'd find on Earth. And here you can see the wheels, sort of with great trepidation, going down. And all of these little red areas are where we stopped to rat the surface and take chemical measurements. What we find is that although there's 6 meters of sediment, it pretty much has all the same kinds of characteristics that I told you about. That is, we have evidence for a sustained history that must be, at the very least, thousands of years long and possibly millions of years long, where episodically water was coming into this basin and drying up. Well then, if that is the picture of the Martian surface fairly early in its history that we're getting from Meridiani Planum, what does that suggest to us about biology? I have to tell you, I love this picture from the Weekly World News because it rather inadvertently says something important. I must admit, I can't imagine the editors of the Weekly World News ever intentionally said something of importance on the cover. But what they show is, they say, new photo of Mars life, and so what do they show? They show a grasshopper. And what that it sort of intuitively tells us is that we are conditioned to think about life that is very much like ourselves. And we really don't have any assurance that that would be the case where other places where life might arise in the universe. In a sense, it's not crazy to look for what you can understand, but we have to be very careful to understand that biology that arises in other places may or may not have the same suite of characters that we associate with biology on this planet. What that means in terms of exploration, to a first approximation, we should have a very good idea of the capacity of physics and chemistry to make chemical and physical patterns on a planetary surface. And it's only when we find something that can't be explained readily by those kind of processes that our antennae go up and we think about biology. Now I love these little headlines that I actually took from the web on the day when it was announced that there were crossbeds on Mars that showed evidence for running water. I have to tell you that the word life was not mentioned in that press conference. So when you go on the web that night, MSNBC said, Rover reveals Mars was once wet enough for life. CNN said the red planet may have been hospitable for life. And the New York Times, ever more discerning than others, said Mars could once support life. Scientists now say, but did it? Well, did it indeed. The one way, in the absence of direct detection tools for paleontological, micropaleontological tools on Mars, we can address this is by saying, okay, we have detected evidence of an environment that was acidic, hypersaline, and only intermittently wet. If we go to environments like that on Earth today, do they support biology? And the answer is yes. This picture that you see of this brilliant red water is from a place called Rio Tinto in southwestern Spain. Now, Rio Tinto comes by its name honestly. It is a Tinto Rio. And the reason it is red is because this water, it has a pH of about 2. And under those conditions, it can actually carry oxidized iron in solution. So the water is this brilliant ruby red. And parenthetically, I would guess if you had been at Meridiani Planum 3.5 billion years ago when it was wet, you would have seen this ruby red water. It's something to think about. What's interesting is if you actually look at there's sort of orange that's forming on the rocks where these waters are flowing in the Rio Tinto. One of the main salts that's forming there is jarosite. So here's a place that has jarosite, iron oxide minerals, other sulfate salts, very much the same suite of minerals that we find in Meridiani Planum. Is there biology there? Yes, there's biology everywhere in there. There are diverse bacteria, there are diverse algae and protozoans. Many, many different groups of organisms have figured out how to live under acidic and episodically dry conditions. So in a sense, the first order answer to the question, would the Meridiani playa, if you will, have been habitable, has to be yes. Now that's a qualified yes. I'm sweeping a number of potential problems under the rug, but at least we have some confidence that confronted with this environment, there is no shortage of Earth microorganisms that could survive in it. But what that tells us is if life was on Mars at some time, it might well have adapted to these conditions. There are potential problems, however, when we ask the question, could life have originated under environmental conditions like those at Meridiani? And again, we can address that because there have been 2 generations of chemists who have done experiments in what sometimes is called prebiotic chemistry, that is trying to understand through chemical experiments the kinds of reactions that could take us from simple inorganic gases to the kinds of biologically interesting organic materials that are the building blocks of life. And when we first figured out that we were in an acidic environment, I went to all my friends who do prebiotic research and said, what happens to these experiments under acidic conditions? And they all looked horrified. They said, no, we would never do those. We would never ask a graduate student to do that because they have to get a job someday. And the reason they don't do it is they don't work. You can think of a number of the important reactions that have been known really for up to 100 years on how you generate organic building blocks of life from simple inorganic precursors. There's something called the formic acid reaction, which is a way of generating sugars. That won't work under acidic conditions. There's a reaction where you take hydrogen cyanide and condense it to generate purines, which are part of the materials that give identity and information to RNA and DNA. They won't work. There's something called the Strecker synthesis, by which you can generate amino acids from simple inorganic precursors. Again, amino acids are the building blocks of proteins. That doesn't work either. In fact, if you have things like proteins and DNA, they actually will break down under acidic conditions. And so it turns out that if the Martian surface was broadly similar to what we find at Meridiani early in its history, it is hard to imagine, at least knowing the chemistry that we know today, that that would have been a very hospitable incubation place for life. Now, the other way to say that, which is maybe a little more hopeful, is that if life did arise on Mars, it must have arisen through a chemistry which, A, we don't understand very well, and B, must have been different from the chemistry we envision for the genesis of life on Earth. And that would suggest that any biology that might have arisen on Mars might indeed have been quite different from Earth. And it gets worse, that the surface of Mars is not only strongly oxidizing now, but was oxidizing 4 billion years ago as well. And the only thing that makes prebiotic chemists more horrified than acid is oxygen, or oxidizing conditions. So while we are admittedly ignorant of many aspects on the origin of life on Earth, and I think are even more ignorant of the kind of chemistry that might run under these particular conditions, what we know now is not terribly promising. So I think one of the questions that we need to ask, and we're going to have to ask it by continuing exploration, is that Meridiani environment unique, or is it in fact representative of most of the Mars surface, and when did it become representative of the Mars surface? There is some good news, and that is when we go to a place like Rio Tinto, we find that the minerals of Rio Tinto really do encrypt a discernible record of biological activity. The picture you see is actually microfossils, tiny little bacterial filaments actually preserved in iron minerals at Rio Tinto. So that if there was life ever on Mars, it might well be recorded in those rocks. And also, we could learn a great deal about Mars's surface history by looking at the chemistry of these sulfate salts and the iron in it. So all of that suggests that in continuing exploration, there will be real interest in a sample return mission to Meridiani Planet, one where you plunk down, grab a sample, and hightail it for home. So, some conclusions then. First, and this is the surest conclusion I can give you, is that life is a planetary phenomenon. It's not something that is different from the planet that it arises on and sustained on. It is part and parcel of the planetary surface system. On Earth, sedimentary rocks tell us that life has a long history, and it is of great interest in light of that Martian sediments also record a planetary history. Based on what we are learning right now in Meridiani Planum on the Martian surface, I think it's fair to say that the question of whether life ever existed on Mars remains open, but the discoveries that are being now made are really constraining our options. I think it is no longer possible simply to make unbridled speculation. And certainly, and this is the other conclusion I'm confident in, that despite claims over the last several decades that although Earth and Mars are different now, they were once very, very similar planets earlier in their history, Meridiani is telling us that by 3 or 4 billion years ago, Mars and Earth had already gone down very different historical environmental pathways. They were different planets early on, and they have simply become more different through time. And then finally, one has to think of this mission, I think, in the context of a program of exploration, one stepping stone, a fairly early stepping stone, I think, in our understanding of a planetary neighbor. And so I anticipate that in coming missions, there's another lander scheduled for 2009, and I think perhaps an over-optimistic suggestion that a sample return mission could be flown as early as 2013 or 2015. There's no question that as NASA begins to think about those missions, that what we've learned at Meridiani will actually cast a very long shadow in the continuing exploration of Mars for evidence of both its planetary and potentially biological history. So thank you very much. If people have questions, I'd be happy to try and address them. And if you're disappointed that I didn't talk about other galaxies or William Shatner or something like that, I'd be happy to try and address them. I will say that I have terrible eyesight, so if you have a question, I won't think you're rude if you just shout it out, because I won't see your hand. Sure. Yep. Yeah, that's a good question. And the question was, since I've made the claim that we have an atmosphere that's 20% oxygen because of life, can you look at the Martian atmosphere? Is there oxygen in it? And if there is, would you be tempted to make a similar claim on Mars? The answer is no, you wouldn't. And the reason for that is the amount of oxygen involved. We do know that there are processes that can make trace amounts of oxygen and could have done so on the Mars and diffusing locally or regionally into the Martian atmosphere. Now, it turns out that there's a variety of ways that you can actually make natural gas. We know there are some types of microorganisms that make it for a living. And most of the methane you would find in the Earth's atmosphere today does have a biological origin. But again, there are non-biological ways of making trace amounts of this gas. And at this point, we have no way to differentiate between them on Mars, but in the very small amounts that are made, no reason to favor a biological origin over a non-biological origin. And this gets back to what I said earlier, that if you want to find something that's ironclad evidence for biology somewhere else besides Earth, you sort of have to find a signal that can't be mimicked by physical processes. Unfortunately, trace amounts of oxygen, trace amounts of natural gas are signals that can be mimicked by non-biological processes.
Dr. Knoll?
Yeah.
The last time we looked for life on Mars was in 1977 with the Viking landers.
Right.
If you were putting together a probe today, what kinds of instruments would you use and what signals would you look for to detect extant life form?
Yeah, that's a great question. Some of you will know that when the Martian lander, the Viking lander, was a spectacularly successful mission in the 1970s, they had a series of experiments. The most important one for biological purposes is one that can be essentially described as taking a cup of chicken soup, adding soil to it, and seeing if anything eats the soup. And I mean that in a very, very direct way. It was actually a very clever experiment. You have a nutrient broth, you put something in it, and then they had a way of actually measuring carbon dioxide that was released into the sort of headspace of the container where this experiment went on. The reason they measured carbon dioxide is that all of you had dinner before you came here, and you ate nutrients, organic matter, and ever since then, you've been breathing out carbon dioxide because the process of aerobic respiration takes that organic matter and oxygen and breaks it down into water and CO2. That's how you get the energy you need to live. It turned out that CO2 was released, but it was not released, people think, by biological processes, because the pattern of release was not the pattern you would expect if you inoculate something like a petri dish and watch the growth of bacterial colonies. It was the kind of sort of time history of release you'd expect if you had some non-biological oxidant. And that is, I think, most people, there are people who still disagree on that, but I think most people accept that a non-biological oxidant is the preferred way of explaining those. Now, one of the things we know now is we have, I think, a much better sense of the variety of bacterial experience than we did even 30 years ago. There are all sorts of chemical reactions by which bacteria make food and energy that if I had put those down as answers to questions in my college microbiology course, I would have failed the course. People would have thought I was crazy, and now we know that there are these wonderfully diverse ways of bacterial metabolism, and they, of course, then give us a wider array of things that we might look for in terms of the products of that kind of metabolism. So I guess if I were going to look for evidence of Martian life living today, I would want things like mass spectrometers that are capable not only of identifying various materials that might be made by biology, whether it be natural gas or CO2 or any of a variety of other products, but also measuring their isotopic composition as the ratio of carbon-12 to carbon-13, which has an extra neutron in it. It turns out that biological processes actually, it's a process called fractionation, they actually change the relative ratio or the relative amounts of those two isotopes in materials that are made by biological processes. So I think we need very sensitive chemical indicators, we need very sensitive isotopic chemical indicators, and I think if we're going to get serious about life on Mars, it is, I think, unlikely, with the exception of what the gentleman just asked about before, it is unlikely that the present day surface is maybe the most likely environment to find active metabolism today. One might look in the subsurface somewhere that will require drilling, and drilling is a technology that, on Mars at least, has a long way to go. I guess if we're going to go to Mars, I'd probably look for this methane and see if we can say something about its isotopic composition relative to that of the CO2 that we see in the same environment.
Dr. Knoll.
Yeah.
Do you think that it's safe to assume that based on the information you've gotten from the small area around the equator to say that that's indicative of what has happened on the rest of the planet? And also, are they developing any other ways to try and explore further outside those boundaries?
Yeah, those are both good questions. Let me answer the second one first, because one of the things that's important about a mission like this is that there are two sets of what NASA loves to call assets that might be used in exploring the Martian surface. One is landers, which are going to give you a very detailed picture of a very small piece of real estate. And the other is orbiters that are going to give you a necessarily broader brush view, but potentially of the whole planet. One of the important things to do on a lander mission then is to actually calibrate those signals you're seeing from orbit so that you can interpret orbital signals with more precision. That's certainly one of the things that was done both at Gusev and Meridiani. The question of, and in fact the Omega, the European Union satellite, is finding now evidence of some of these sulfate salts more widely on the planet. As to the question of how representative, and I think in both time and space, is Meridiani of the Martian planet, that's an important question. It's one that we've been struggling with. And you have to sort of think, what are the elements, the components of the recipe that has given us those features that we see in Meridiani? One of the elements is basaltic volcanic rocks. We know those cover the whole planet. That's not something that is our regional constraint. The second, I think, would be the distribution of oxidized sulfur compounds, and in particular, the likely distribution of any acid that was formed. And there again, I think there's reason to believe that that's likely to be a global process. And I can find people who disagree with me on that, but I think the way that the acid would have been generated on Mars is that sulfur dioxide, a very common gas that is emanated from volcanoes, simply has to run into water vapor, and the result is sulfuric acid. And particularly on a cold Martian surface, that sulfuric acid will actually come out as frost. It'll be a solid. You can imagine sort of a sulfuric acid frost on a cold morning on Mars. Again, the types of processes and atmospheric circulation involved suggest to me, and have suggested to many other people as well, that it's likely that in some way that environment type of acidic component was likely to be widespread. In fact, if that is widespread, it would help us explain one of the great conundrums of Mars, which is why don't you see any limestone? On our planet, with lots of CO2, you form limestone everywhere and have for the last 4 billion years. Nobody has ever found carbonate minerals, calcium carbonate limestone, in anything more than trace quantities on Mars. And one of the questions is why? A potentially very simple answer to that is that carbonate minerals do not form under acidic conditions. And so if the Martian surface is broadly acidic, then you cannot in principle form carbonate rocks. So there's a number of reasons, none of them ironclad, I will admit, to suggest that acidity was also not the regionalizing component. And I should say that one of the things about acid that potentially helps us to explain another conundrum is people who study the relationship between atmospheres and climate and climatic history have struggled for many years to understand how Mars could have been warm enough 4 billion years ago to have water cutting all these channels in the surface. We know from physical models of the sun that 4 billion years ago, the sun was only about 70% as luminous as it is now. So that would have made it even harder to make Mars warm. Again, there's a potentially interesting solution. That is that water freezes at 0 degrees Celsius under Earth's surface conditions. Sulfuric acid freezes at about 2 or 3 degrees Celsius under Earth's surface conditions. But interestingly enough, if you make a mixture of water and sulfuric acid, you can depress the freezing point by up to about 80 degrees C. So if you had a way of mixing water and sulfuric acid on early Mars, you could have actually had at least transient flows of liquid at temperatures that are much, much colder than the temperatures required to have pure water flow. That's kind of an aside. So what I come down to then in trying to answer your question is that I'm guessing, and this is personal opinion, I should say, and not NASA-approved statement, that the most likely thing to have caused that particular mixture of salts and iron at Meridiani was the amount of water that environment saw. And that would suggest that water was probably, even 4 billion years ago, a more dear commodity on Mars than on Earth. In fact, if there was a lot of water on the Martian surface, then all that basalt would have essentially chewed away at the acidity, and you'd probably have carbonate rocks all over the planet. We don't have them. We do have widespread evidence of sulfate salts That suggests there's a little water, but not much. You add more water, you will then redissolve some of the iron sulfate salts and reprecipitate them as iron oxides, like the hematite we see. And so I'm guessing is that the entirety of Mars' surface, pretty early in its history, was pretty dry, but it was relatively wet and relatively persistently wet in Meridiani Plana. That would explain the distribution in space. If you ask the distribution in time, I cannot, in all honesty, tell you that 4.4 billion years ago the planetary surface was acidic. We just don't have any data on that. So it is possible to hold out the hope that in the very earliest history of Mars, it really was wet, and it really was clement, and it really was amenable to biology. But I am, again, still struck by the fact that if there was all this water and clement environments on Mars, even in its earliest history, where are the limestones that you would expect to see?
Dr. Knoll?
Yeah.
On Mars, I know when we first started thinking about life on Mars, many people thought of the proverbial little green man. Right now, when you're looking for life on Mars, do you expect to find simple prokaryotic life forms, or are you looking to more complex life forms?
Yeah. Well, I have to say that, for better or for worse, because I was identified early on as one of the sort of biological consciences for this particular mission, that many citizens of the United States helped me to do my job. I used to get hundreds of emails early on in the mission where people would circle things on a picture, and all sorts of people were convinced that they saw evidence of animal life. Now, I think, it was exciting to me that so many people would be interested, although I think, again, physical explanations are far preferable for all the things that we're seeing. I don't think we have any reason to be hopeful, either now or in the deep past, that Mars harbored something as complicated and interesting as an animal. I think that if Mars ever was a habitat for life, it would have been a habitat for microbial life, and let's face it, for 90% of the history of life on Earth, that would have been a true description of our planet as well. Large, complicated things are relatively recent. Large, complicated things that can actually think about their own history are only the latest instant in time in Mars. And that raises an interesting question about thinking more broadly beyond Mars. There's basically three ways we can explore the universe for evidence of life. Things that in our own planetary neighborhood, in our own solar system, we can actually go there and do direct exploration. Potentially we can find evidence of almost any kind of life and characterize it if it's there. Beyond our solar system, it is unlikely that in, I would say, the lifetime of our grandchildren, that we're going to go there. So what we really have to do is rely on remote sensing. And as many of you will know, I think one of the truly most exciting things that's happened in science in the last 5 years or so is the detection of an increasingly large number of stars in our galactic neighborhood that have planets rotating around or revolving around them. And in fact, within the next 10 years, it is very likely that we will actually be able not only to detect Earth-sized planets around nearby stars, but actually using remote sensing tools to actually characterize their atmospheres. That opens up the possibility that you could detect life by dint of its impact on the planet that it's on. You wouldn't be able to tell whether it was plants or bacteria. You wouldn't be able to tell whether there were paleontologists there. But you might be able to tell that there was biology because of the composition of the atmosphere. But even that's only going to take us out a very short way into the universe. And I think it's fair to say that for the rest of the universe, the only way we're going to know if there is biology out there is if somebody calls us and tells us. So it's kind of ironic in a sense that the type of life most likely to be widespread in the universe is a type of life that we can only search for in our immediate neighborhood. And the type of life, at least in relative terms, most likely to be rare, is the only type we can search for in the universe at large.
And no one is likely to call us and tell us tonight.
You never know.